Section 6.1. Welcome to Chapter 6. In this chapter, we're going to take a pretty different approach to solving differential equations than what we've seen in the previous chapters. Specifically, we're going to try to utilize power series representations of functions as a tool for solving differential equations. I know that power series and series representations of functions more generally are not the most popular, the most well-liked topics in a calculus sequence. So maybe this is something that you learned a couple semesters ago and you've kind of tried to forget since then. But series representations of functions are in fact quite useful, practically useful, and show up in lots and lots of different contexts. So our goal in this chapter will be to see how they can be used to solve certain differential equations. In this lecture, we'll review some of the basic properties of series representations of functions in an effort to build up towards section 6.3. In section 6.3, we will demonstrate how we can use a series representation of a function as a tool to solve a differential equation. So let's start by reviewing some of the basic properties and characteristics of power series. As I've indicated here, I think of a power series, or more generally, some series representation of a function as essentially a series which contains the independent variable raised to a positive integer power in each term. The coefficients on those power terms are going to be usually given by some formula, and so we'll be able to compute them in a predictable way. And there's a few different ways of writing these, but essentially I think of these as polynomials. And that's kind of the strength, that's kind of one of the nice features about using this type of representation, is that we are essentially representing a potentially complex function, some function that could have lots of strange properties and could be difficult to deal with. But instead of dealing with the original representation of the function, we're going to represent it as a polynomial. And in terms of calculus, polynomials are some of the easiest functions that we could possibly deal with. And the one thing, of course, that makes these potentially different from traditional polynomials is that they could have infinite degree. So let's take a look at some examples. I've got 4 examples here, and I just want to highlight some properties and just kind of remind ourselves about the structure and nature of a series representation of a function. This first function, f of x, is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So the first thing I notice is that my power terms only have odd powers. And so whatever the structure or nature of this function is requires that I only deal with odd powers of x. And then there's some symmetry. The denominator is the same as the exponent, but then a factorial. And then we're alternating between plus adding and subtracting, so plus and minus. So a pretty straightforward representation. In fact, this is a pretty common series, and you may recognize this. But for now, that's not really my goal to be able to identify that. So I'm just going to kind of leave it as it is for now. How about this second example? Once again, I've got a real predictable pattern to my coefficients. They're simply increasing by 1 every time, 1, 2, 3, 4, and they're also alternating between positive and negative. And then the powers on x are just increasing with each term. In this third example, one difference that I notice here is that now the variable term is not strictly in terms of x, but is instead written in terms of x minus 1. So here, this x minus 1 is kind of acting like the independent variable. Here I have it again, but it's raised to the 2nd power, here to the 3rd power, etc. So one feature that I'll just point out about this particular one is that this series has a center of 1. And hopefully you remember this terminology. We would say this series is centered at 1, and I'm picking off this 1 here. And so if I ever have a series that's written as x minus some value, then I would say that that numerical value is the center of the series representation. What about the first 2 examples? We didn't mention that detail at all about those. If you think about each of these, we could take the perspective that this x to the 7th, as one example, is really x minus 0 to the 7th. So both of these first 2 examples could be thought of as being centered at x equals 0. And just in terms of the notation, I'm accustomed to writing the center as x sub 0. In every case, that's just a variable that I'm used to using for that center value. There's different ways of writing it. Sometimes you simply say a equals, but this is what I'm accustomed to doing. And then in my fourth example, maybe this is the form that you're more accustomed to. I've actually written a closed form expression for what each term looks like. I've got my power term here, x to the, notice there's kind of a lot going on in the exponent, so I don't think I'll get every positive integer value for x showing up in my series. And then these other terms are essentially defining the coefficients on the series. In fact, if I wanted to make that structure a little bit more obvious, I could rewrite this general term in here, and then I can see clearly that I've got x to a power, and then this coefficient formula is determining what the coefficients on each term would be. If I wanted to, I could plug in small n values, start at n equals 0, plug in n equals 1, n equals 2, and I can write out several of the first terms of this series so that I would get an expression for this series that's similar to what I've seen in the first three examples. So I believe if I plug in some preliminary n values, for example, plugging in n equals 0, I'll have negative 1 to the 0, which is 1, and then 2 times 0 plus 1, which is 1 factorial. And then this variable term will be x to the 4 times 0 plus 3. So simplifying all of that, I just get x to the third. Then plugging in n equals 1, n equals 2, n equals 3. I believe these are the first few terms that I get. So this last example I have represented in the two different ways. On the one hand, I have the closed form expression. I will typically call this sigma form because it's got this capital sigma here. And this is a little tidier. I can write the entire series and just this one term here. But often it'll be helpful, especially for what we're trying to accomplish here, to actually write out several of the terms of the series. So while you may be accustomed to dealing almost exclusively with series as represented in this sigma form, in many of the examples that we work, we'll actually use this sort of written out form instead. But a series can always be represented in both ways. In fact, let me back up to one of my previous examples about this second example or third example here. And let's see, what's the pattern of my coefficients? Looks like it's always 1 over 2 to a power. And then my variable term is x minus 1 to that same power. So here I have 1 over 2 squared, x minus 1 squared, 1 over 2 cubed, x minus 1 cubed, etc. So I could represent this series in this closed form, sigma form, if I preferred to. I could do the same thing for the first two as well, but again, that's not exactly my intention. At this point, I just wanted to use these to demonstrate and kind of remind ourselves of some properties of series representations of functions. In this next paragraph, I just point out that sometimes our goal is to actually relate a series representation of a function to a known or established or common function. Things like sine of x, cos of x. That is to say, maybe I have sine of x and I want to try to find or calculate or compute a series representation of that function. Or maybe I have some slightly modified version of sine of x, and my goal is to come up with a series representation of that known function. Or maybe the goal is reversed. Maybe I have a series representation and I want to try to identify what known function that is associated with. As I said, this is a common goal, and we'll do that a little bit in some of the examples that we look at in this section. But that goal is typically accomplished through what are called Taylor series. And for our purposes, in terms of what we're trying to accomplish in Chapter 6, Taylor series don't play a really big role in the methodology that we're going to use. And so instead, we'll mostly deal with series representations written out term by term, or at least a few of the terms written out explicitly as the desired form or desired representation of our function. And in the last paragraph on this page, I just kind of give a little defense of series representations of functions. I know, especially when students are learning this for the first time in calculus, this all feels very strange and it feels unsatisfying in some way. to have a representation of our function that involves essentially infinitely many polynomial terms. And in my experience, there's always some students that have a hard time coming to grips with that, or at least seeing how that could potentially be practical or useful. So what I just point out in this last paragraph is that there are in fact lots of contexts where we don't need a perfect closed form description of the solution to our problem. Instead, we essentially need a good approximation of our solution. And one way to accomplish that is to find a series representation of our solution. And then while technically that series representation does include infinitely many terms, we may be able to, for the purposes of a specific problem, identify the solution to some required level of accuracy by simply taking the first several terms of the series. We won't take time in this chapter to kind of walk through that process, but I just wanted to, as I said, defend series a little bit and just make the point, reiterate the point that these are in fact quite practical and they do get used in lots and lots of different contexts. At the top of the next page, I've pointed out some terminology that I hope you're familiar with, but I just want to remind you of these definitions. It is very important for us to be mindful about where a series representation that we build will converge. And so we define the interval of convergence for a series to be the set of input values, or the set of x values, for which that series converges. Oftentimes, this has a specific structure. What I've noted here is a set of all x such that x minus x naught, remember this x naught or x sub 0 represents the center of our series. So this inequality is telling me that the distance between an x value and the center is less than some capital R value. And in some cases, it could potentially be equal to that capital R. The capital R is called the radius of convergence. The term radius here may feel a little out of place because we're used to associating a radius with a circle. But the idea is that we go out R in both directions from x sub 0. And so this inequality defines an interval of x values on which our series will converge. How do we determine the interval of convergence, the radius of convergence? There's two tools, but the primary tool that we utilize is what's called the ratio test. Again, going back to calculus, you remember hopefully a whole host of tests that are used to determine whether or not an infinite series converges. We're not going to spend the time here to remind ourselves of all of those different tests. I essentially want to focus in on this specific test, the ratio test, because it plays such an important role for us in terms of determining the radius of convergence. So here's one way to state the ratio test. If we are given an infinite series, here I've stated it pretty generically. I just have some general term b sub n, and I'm adding that from n equals 0 to infinity. Then the first thing I want to do is I want to compute the quantity, which is the limit as n grows without bound, of the absolute value of the ratio of two subsequent terms in our series. It's convenient to name that quantity something, so it's customary to say, let's call that capital L, and then the value that I get for that limit determines the convergence or divergence of the series, maybe. So now as I'm looking at the notes here, I notice a very blatant typo. It is of course impossible for that quantity to be less than 0 because I've taken the absolute value. All of these zeros here should be 1s. There, that's a little bit better. And so, as I was saying, if I calculate this limit and it turns out that that limit value is less than 1, then my series converges. If that limit value is greater than 1, the series diverges. And if the limit equals exactly 1, this test is inconclusive. This test does not tell me whether the series converges or diverges. If that's the case, I have to rely on one of the other tests that we discuss when we're investigating the convergence of series. Remember that the series that we're talking about are power series, and so I expect this general term here to actually have an x to a power, like the examples that we saw above. And so when I compute this value L, I expect there to be x to a power involved in this expression, and that will lead to an inequality that has this structure that we highlighted a second ago. So let's take a look at a couple of examples to see how this plays out. In example 1, part A, I have borrowed one of the sample power series that was given as an example earlier in the lecture. And I identified just a moment ago that if I wanted to write this series in a closed form expression, or in this sigma form, I could write it this way here. And that will be helpful because that will allow me to identify explicitly what the b sub n is that I will use in the ratio test. Specifically here, I'll have the terms of my sequence, the term that I'm adding up, the terms of my series, are actually given by this form here, given by this expression here. So in order to apply the ratio test, I will compute this limit quantity, the limit is n grows without bound, of the absolute value of this ratio, and then I will compare this limit value to the reference value of 1 to determine where the series will converge. So plugging in my particular expression for b sub n here, and you'll notice, I'm not sure if you're accustomed to doing this, but instead of trying to write one big fraction, which would be a fraction of fractions, I typically take this numerator, which is the n plus 1th term, and I write it out. And then instead of trying to write divided by the nth term, I multiply by the reciprocal of the nth term, which is of course equivalent to division. So as you remember, there's always some simplification that occurs here. Looking at these 2 to a power terms, for example, I have 2 times itself n times in the numerator. In the denominator, I have 2 times itself n plus 1 times. So based on properties of exponents, those will simplify and I'll be left with 2 to the first power in the denominator. That factor 1/2 is actually constant with respect to this limit, so I can bring it outside the limit. It's also positive, and so I don't have to bother writing its absolute values anymore. And then applying that same technique to these variable terms, it looks like I'll have an extra x minus 1 to the first power in the numerator. I don't know if x minus 1 is positive or negative, therefore I have to retain these absolute value bars. The next step is to evaluate the limit as n grows without bound. Well, actually, because of all of the simplification that took place, there are no more n's in this expression. So as n grows without bound, this is simply x minus 1. So the value for this key limit expression reduces to 1/2 times the absolute value of x minus 1. Next, I actually want to force this series to converge. A divergent series isn't particularly interesting because I can't draw any conclusions about it because it doesn't converge. And so using the properties or the thresholds from the ratio test, I know that I want this limit value to be less than 1. If this limit value does turn out to be less than 1, then I know that the series will converge. I can easily manipulate this inequality by just multiplying by 2, and that gives me an interval on which my series will converge. More specifically, this inequality is telling me that my interval is centered at 1, and then I go 2 in either direction, above and below 1. So for values between -1 and 3, I know that this series will converge. Often it is sufficient for us to stop at this point. We've identified that our radius convergence is 2. We know what the center is. We actually knew what that center was from the original statement of the series. And so in many cases we can simply stop here and use the open interval from -1 to 3 as our interval of convergence. That is to say, we exclude -1 and 3 from our interval. You may remember that we can actually push this a little bit further to be a little bit more thorough and test the convergence of the series at these individual endpoints. Here's what I mean. I'll consider each endpoint individually. So here I'm looking at the left endpoint, x equal to -1, and I can take that x value and plug it into my original series. My original series was x minus 1 to the n over 2 to the n. Here, since I'm considering a specific x value, I can plug in that particular x value. And now I simply want to ask if this resulting series converges or diverges. Doing some simplification, I actually can rewrite this series as simply negative 1 to the n. Now, thinking back to calculus, I know that this is a geometric series and that the ratio of this geometric series, the r value, is negative 1, and a geometric series only converges if that ratio, the r value, is strictly less than 1. Therefore, I can conclude that this series diverges based on properties of the geometric series. I'll repeat my analysis at the other endpoint at x equals 3. And I can once again conclude that that particular endpoint needs to be excluded from the interval of convergence because the resulting series does not converge. Therefore, both of these endpoints are excluded, and my final interval of convergence will be the open interval from negative 1 to 3. So the main takeaway from this example is just demonstrating, hopefully reminding you of the process of applying the ratio test to determine the interval of convergence of a power series. Let's try that again in part B. I have once again identified b sub n explicitly, and now I will apply the ratio test and use that b sub n as I build the necessary fraction. Here I've used that stated b sub n to plug into the formula as necessary, and as I'm accustomed to, I've written b sub n plus 1 as a fraction here, and instead of trying to divide by b sub n, I simply multiply by the reciprocal. Now I'm used to there being some simplification. Let me go ahead and line up the terms in the numerator and denominator that are similar. This arrangement of the terms just makes it a little easier to see what will cancel from this first fraction. I'll be left with negative 1 in the numerator, but since I'm taking the absolute value will essentially cancel that negative 1, so I won't have anything that remains from this term. Looking at this second fraction, I've got two factorials, and you remember, of course, that factorial means we're going to take the number 2n plus 3, for example, in the denominator, multiply by the next smallest integer, and then the next integer after that, etc. In this particular case, if I was to start writing out those terms, I would have 2n plus 3, and then the next smallest integer, which is 2n plus 2, and then 2n plus 1, and then 2n minus 1, etc. But it's convenient in this case to write all of the terms after 2n plus 1 as simply 2n plus 1 factorial, because now I see that that 2n plus 1 factorial will cancel with the 2n plus 1 factorial that I have in the numerator. So this fraction will simply be 1 over these two components here. Lastly, I have x to a power and x to a power. I can simply subtract those two powers, and it appears that I'll be left with x to the fourth. So now I'm ready to evaluate this limit. As n grows without bound, x to the fourth is unaffected, but this fraction here has n terms in it, and as my n grows without bound, that is, as I evaluate this limit, the denominator of this fraction will grow infinitely large, while the numerator remains constant. Therefore, the overall value of this limit is 0. And notice that this is true no matter what the x values are. Since 0 is less than 1 for all x values, that means that this series will converge for all x values, because the ratio test asks whether this limit will be less than 1. Therefore, we can conclude that this series will converge for all x values. Another way of saying that is that my interval of convergence will be from negative infinity to infinity, or I could say that the radius of convergence is infinite. Let's go ahead and take a look at the next example. Actually, before we get into example 2, there's a short paragraph here just indicating that our goal for the remainder of this section is to discuss a couple methods that we can use to modify established series representations. So the idea is that we have somehow built a series representation for a function, or one's been given to us, and we want to perform some allowable operations on that series. For the purposes that we'll be trying to accomplish in this chapter, there's really only 3 operations that we want to highlight. First, we'll discuss modifying the indices of a series. This actually isn't making a change to the series itself. We're still using the exact same series. It's just a change in how I've chosen to label that series. We'll see some examples of that. Secondly, we can multiply a given series by powers of the variable x. And lastly, we can differentiate a series. If we can differentiate, we can also anti-differentiate, and so those two operations kind of go hand in hand. These modification techniques are demonstrated in the next couple of examples. So for example, here in example 2, we're simply asked to take this series, this given series, and rewrite it so that the starting index is n equals 0. First, this isn't really a necessary step, but just to clarify kind of what's going on with this series, I'd like to just write out the first several terms of this series. And there's of course some simplification that I can do here, but I just wanted to write this out to make the structure of each of these terms very, very explicit. I also will just point out that we've got this unknown term a sub n, and in a sense that's kind of a variable, and this will be a feature of the problems we solve later in 6.3. So now, as I said, my goal in this problem is just to rewrite this in sigma or sum notation, but to do so in such a way that my starting index will be 0. But it's important to note that I'm not going to change this series at all. So I still need to get all of these exact same terms. I just have to rewrite the definition of the series in such a way that I'll get all of these same terms, but my index will start at 0 instead of 1. And this isn't too tricky. For example, I need this coefficient to be 1. Well, when I plug in the very first index, I'll be plugging in a 0. So instead of that coefficient simply being n, I would need that coefficient to be n plus 1. Same is true with the index on this unknown coefficient or constant term. Here, the very first term in my series is a sub 1, and I need to get that out if I plug in n equals 0. And I can accomplish that by just making that index 1 larger. Same idea with this exponent. If you look, when I simplify this exponent, I actually get 0 in the exponent, and then I get 1, and then I get 2, etc. So the exponent on this x minus 3 term could simply be n. And that's it for this problem. I'm not going to do any more computations or modifications. I just wanted to, in a real simple way, demonstrate our ability to rewrite a given sequence by just modifying the index. And then note that effectively, in order to move my index down 1, my starting index down 1, all of the n's in the definition of the series terms had to be increased by 1. That's pretty intuitive. So as I said, that'll be a feature of a lot of the problems that we deal with later in the chapter. Example 3 asks us to do something pretty similar, except I've got a few more terms involved. I've actually got 3 separate series, and my goal is to modify the index, if necessary, so that I can somehow combine all 3 of these series. Essentially, that will involve trying to get all of these power terms to the same power, and then, if you could imagine, factoring that out of all 3 sums, and then that would enable me to write that power term once in a single sum with the associated coefficient expressions multiplied. Before I start working on that, one detail to point out is that this second series has an x minus 3 kind of acting like a coefficient. That x minus 3 can actually be distributed into the series, and so currently each term in my series has the form x minus 3 to a power. If I multiply every single term by x minus 3, that'll increase the power on all of those previous terms by 1. So I can see that I actually have in this second series an unknown coefficient expression a sub n again, and then multiplied by x minus 3 to the n plus 1. On this third series, I have a 3 that I could distribute through to every term in the series. That's not as significant as distributing in this variable sort of coefficient, but I'll go ahead and push it into the series anyways. Now I notice a couple things. First of all, I notice that in this series I do have an x minus 3 to the n plus 1, whereas in this series I have an x minus 3 to the n. My goal will be to get all of these to agree. Therefore, as I'm looking at this first series, I think it would be best to try to somehow modify this so that I will also have an x minus 3 to, I guess maybe I'll try to make everything look like x minus 3 to the n. So what that means is that this exponent needs to increase by 2. If this component is going to increase by 2, then all of the other n components will also need to increase by 2. And that can be accomplished pretty easily as I have here. But then the kind of flip side of the previous example is that if these components increase then the starting index needs to decrease by a corresponding amount. That's not hard to do. I can simply make this n equals 0 since I have increased all of the n values in this definition of the series terms. And we can easily verify that this is an equivalent expression. Imagine plugging in the first index here. The first index originally was n equals 2. If I plug that into this series, the first term that I'll get will be 2 times 1 times a sub 2 x minus 3 to the 0. And in this expression, if I plug in the first index, I will also get 2 times 1 times a sub 2 times x minus 3 to the 0. So it's typically when we make these sorts of modifications, it's pretty easy to verify that we've done that correctly. All right, at this point, I've got two like terms, x minus 3 to the n. And so these two series, I'm ready to kind of combine in such a way that I can write them as a single series. This particular series, I can't accomplish that quite yet because I have a higher power on that x minus 3 term. One way to account for that would be to simply change the values in this definition of this series, that is, decrease each of these by 1. That would lead us to increase this starting index by 1. And I can accomplish that just kind of using the method that I have seen in the previous example and that I used on these terms here. Specifically, what I'm going to do is I'm going to decrease these n values within the definition of the series terms by 1, and that'll lead me to increase my starting index by 1. That'll give me this series here. Let me copy down my other two series just for reference. And now all three series have been modified such that the power terms match. Unfortunately, I'm not quite ready to combine these yet because the starting index on these three series don't yet match. If you think about it, this term will start at n equals 0. I'll get a certain value, whereas this does not have an n equals 0 term. This third one does in fact have an n equals 0 term. So in a sense, the first and third have extra terms. There's a couple ways to account for this. I think the easiest way is to simply figure out what those extra terms are and peel them off outside of this full sum and then write the remaining terms of the sum. Let me show you what I mean. I'm going to write the n equals 0 term from this sum all by itself. And then I'll write the remaining terms from n equals 1 on to infinity in this standard sum or sigma notation. Now, as I compare this series expression with this second series expression from the previous line, I can see that not only do the power terms match, but the starting indices match as well. So now these two series are on equal footing in a certain sense. At this step, this second series is just along for the ride. And then for the third series, I will once again peel off the extra term as I did with this first series here. The extra term here when n equals 0 will be 3 a sub 0 times x minus 3 to the 0. And then the remaining terms for n equal 1 through forever, I will once again write in this standard sigma notation. So now I have all three of the series written in such a way that their starting indices match, and more importantly, written in such a way that these power terms all agree. Now again, imagine actually writing out all of these terms, and you'll see that every single term here has an x minus 3 to a power in it. Similarly, all of these terms, and because everything in these three series matches up perfectly, the powers on those terms will match. So what I can do next is essentially factor out that x minus 3, which will leave me with these coefficient bits here, and then write this as one conglomerated sum. So here I've done exactly that. First I took these extra terms and did some simplification and then just moved those out front of the series. And then the remaining three series I've kind of coalesced into one final series here. In a sense, I've factored out this x minus 3 to the n term, and that leaves me with these coefficient expressions that were originally in the three separate series, now being added together to make the one overall coefficient expression for for this single series. This process might be a little strange. It's a little unclear why we're trying to do this necessarily, but as it turns out, this is kind of the key step in 6.3 when we're using series to solve differential equations. So for the purposes of this problem, though, we're going to call it there. We'll say that we're done, and that's our final answer. All right, we'll finish off this section with two quick examples of this third method of modifying a series that I discussed earlier, namely taking the derivative of a given series. And on the one hand, this feels a little intimidating because I've got infinitely many terms, but on the other hand, each of these terms is simply a polynomial. In isolation, the derivative of each of these is really straightforward. What's the derivative of x? It's just 1. What's the derivative of x cubed? It'll be 3x squared. And as it turns out, in order to differentiate all infinitely many, I really just think about going through term by term and taking each individual derivative. So here I've done exactly that. I've just gone through and applied the regular power rule to every one of these polynomial terms, and this is it. This is my final answer, f prime. In this particular case, there is some simplification I can do. Here I've got a 3 divided by, remember that this is 3 times 2 times 1. So the 3 in the numerator and the 3 in the denominator will cancel. So my denominator will simply be 2 times 1, or 2 factorial. So I can simplify that derivative to look something like this. And that really is all that I wanted to kind of demonstrate on this example. Before I move on to the last example, example 5, there is one thing that I'll point out. Some of you may remember from calculus that this power series is a famous function. And then now that we've taken the derivative and we look at this power series, some of you may recognize that this is a famous power series expression as well. So let me just go ahead and name exactly what those are. So in this first series for f, or what we've labeled f here, where I just have odd powers of x, and the sign is alternating between positive and negative, and then the denominator is the same as the exponent but the factorial. You may remember that that is actually the series representation of sine of x. And the series that we have for the derivative f prime, where I just have even powers of x, again the signs alternate, etc., that turns out to be, hopefully not surprisingly, it turns out to be the series representation of cosine of x. So we know that if f is sine, then f prime equals cosine, and then this just reiterates that that relationship holds as well in terms of their series. All right, let's take a look at the last example. On example 5, I'm once again asked to find a derivative. This time I don't have the terms listed out. I have the sigma or series form of the series presented. But I just wanted to use this example to remind you that the standard differentiation rules can apply even if I'm dealing with a function that's written in sigma form like this. If we think about taking this derivative, well, I'm differentiating with respect to x, so this -1 to the n as well as the 2n plus 1 factorial are both just kind of coefficients. They're just along for the ride. And so this x to a power term is the only term that I'm really thinking about differentiating. And when you differentiate x to a power, you bring that power down and you subtract 1 from the power. So I can write the derivative of this power series simply as, again, these coefficients, -1 to the n, 2n plus 1 factorial, those are both just along for the ride. And then here I have brought the previous power on x, 4n plus 3, brought it down as a coefficient, and then subtracted 1 to get my new power on x. And that's it. That's all I wanted to demonstrate with these last couple of examples. So in this section, I just wanted to remind you of some of the key properties and characteristics of series representations of functions. And we're going to build on this, and the goal is in 6.3 to use these types of properties, these types of techniques to actually be able to solve differential equations.